for inviting me to this very interesting workshop of complexity. And today I'd like to talk about a quantity which we call pseudo entropy, holographic pseudo entropy, which is a kind of generalization of holographic entanglement entropy and some analogous quantity about complexity, which in the end I want to discuss in this talk. But I apologize that maybe 80% of my talk is about this entropy, the pseudo entropy, but in the final 20% of my talk, I'm going to talk on and discuss about the holographic complexity counterpart of this our proposal. And this work is based on our recent preprint, here. So this is a later pointer. And so based on the collaboration of Yoshifumi Nakata and Yusuke Taki and Kotaro Tamaoka and Disha Wei. Okay, let me go on. And let me start with the quantum entanglement. I think most of you are very familiar with this, and there are many experts of this. But the quantum entanglement appears in quantum mechanics, and when we have some if we have some quantum mechanical correlation between two-body systems like A and B, so the simplest example is a two-spin, two qubits. We have a Bell state, which is maximally entangled state between two spins, and this is a minimum unitary. So this is the simplest Bell scale, and this gives some minimum unit of quantum entanglement is maximally entangled two-qubit system. And we say some pure state is there non-zero quantum entanglement if the state is not just factorized into direct product state. And the best measure of quantum entanglement for pure state is mixed state is more complicated story. But for pure state, which we are going to talk about, is the best measure is known to be the entanglement entropy. And entanglement entropy measures the number of Bell pairs between A and B, basically. And so here is our conventional definition, especially fine energy people, including me, and uses quite often in the calculation of entanglement entropy in quantum field theory. And we decompose Hilbert space into two parts, HA and HB. We can do some, for example, if we think about some spin system, we can decompose just picking up some particular spin, we could just call A, another part of the spin is B, and then naturally we decompose this Hilbert space into direct product. And in quantum field theory, we just need to specify the subsystem A and B by spatial region, and by specifying some boundary of A, which is same as boundary of B, then we have also have a decomposition. And then we introduce this reduced density matrix by tracing out some part of the space, which is B, and we just focus on A. Let's assume observer is sitting A. And then we have this coarse-grained density matrix, which we call the reduced density matrix. And we can define entanglement entropy by just standard von Neumann entropy, rho log rho. So this is a way to calculate entanglement entropy in quantum field theories. On the other hand, if we look at the quantum information textbook, which will be also quite useful for later purpose, because we want to generalize this entanglement entropy for transition matrix, which I will explain. In that case, entanglement entropy has a nice definition from the viewpoint of this operation called LOCC, the basic operation. So we assume some two-body system A and B, and they are far apart. They are independent laboratory. And we can do some quantum operation and individually laboratory A and laboratory B. But we can only connect A and B by classical communication, like sending emails or just making phone call. Because they are so far apart, it's not possible to do any sophisticated quantum operations. So inside A and B, we apply some local quantum operation, which is called LO, local operation. So there's a projection measurement or unitary transformation or generalized operations. But we can have some classical communication between A and B. So these are totally called LOCC operations. And the basic example of LOCC protocol is quantum teleportation. And by using this LOCC, we can beautifully define this entanglement entropy, like here. So we start. So we should start from infinitely many copies of the pure state. So psi is a pure state, but if we just look at one side, then maximally we can accept only one unit of this quantum entanglement, namely Bell pairs. But to get some continuous number of entanglement entropy, we need to take an infinitely many copy of the system, which is what we call, people call this asymptotic limit, and then act LOCC for this very large system and copy of the original system. And each system originally very entangled in very complicated way. We have A spin and B spin, but they are very complicated. But after acting some appropriate LOCC procedure, we can extract some nice Bell pairs from them. It's EPR pairs. So these are just genuine EPR pairs. And we can just count number of this maximal number of Bell pairs which we can extract from this system by LOCC. And this is, let's call this number is n, and we take a originally n copy of the system. Then, so we can take this ratio. This is basically average number of the Bell pairs which we can extract only single copy of this original system. And this is, we take this limit. And then there are a very famous theorem known in quantum information, but I will give some simple evaluation of this in more generalized setup later. But this is just equal to this previous definition, which more high energy people are more familiar with. This low log law is precisely the same. It's like a quantum analog of this Shannon theorem of quantum information entropy. And so this is quite a very beautiful result, and we want to think this kind of idea in a little bit generalized context, and that is the main interest of this talk. And I want to also discuss some similar idea for complexity theory. And so here, so far, I just talk about the quantum many-world system. Now switch to holography. So as you know, holography already explained in Rob's talk, for example. And the holography relates to different theories. So one is a gravity, some d+1 dimensional gravity. This gravitational theory is equivalent to non-gravitational theory, and typically some quantum many-world system, or typically some quantum field theory, and especially conformal field theory, and which lives on one dimension lower space-time. And they are equivalent. This is a holographic statement. And we want to use this holography to evaluate entanglement entropy, also complexity. And for this, there are some two versions, which first I'd like to review two versions of this holographic calculation of entanglement entropy, version 1 and version 2. So it's a static system and time-dependent system. And I want to give some third possible version of this formula. And so, this is the ADS safety correspondence. And so ADS safety correspondence relates this gravity in d+1 dimensional anti-de Sitter space equivalent to d-dimensional conformal field set, and which lives on the boundary of ADS spacetime. And we especially interested in the case of classical gravity limit. And there's that negative cosmological constant, classical gravity, general relativity limit, and that corresponds to the strongly coupled limit in conformal field theory and the large N limit. And so we get some strongly interacting large degree of freedom of this quantum field theory. And the basic correspondence between this side and the other side, gravity side and conformal field theory, is a partition equivalence of partition function or free energy. And this is known as bulk to boundary relation, GKPW relation. And these are ADS safety correspondence, and I would like to go to entanglement entropy, calculation of entanglement entropy. And version 1 is this holographic entanglement entropy for static space-time. So if we just take some static, for example, typical example, one typical just anti-de Sitter space, it's static. There are killing vector in time direction. And that case, actually, so we can just focus on particular time slice, t equals 0, for example, this time translation. In that case, we have a nice Euclidean geometry, just namely hyperbolic space, one dimension lower, but it's hyperbolic. In that case, we can think about this kind of correspondence. We have region A and region B. We take a time slice already. And this is a subsystem A and B, and we define entanglement entropy for region A. And region B is outside. And in that case, actually, we can calculate entanglement entropy by extending this boundary of A towards the bulk. But if there are many different ways to extension, so we just pick a particular one, namely minimal area surface. That is, we compute this area and we minimize it. We always, I would like to call this surface gamma A. A is this subsystem A, and its gamma A's boundary is same as A's boundary. And there are also homology constraints. This homology gamma A is homologous to A. And so anyway, we have to minimize this area. This is basically this static setup. And this is the ADS metric, and we have some warp factor, and this is a warp factor 1 over z squared. This is a metric, and we need a UV cutoff. And in general, this entropy is UV divergent, but we can cut out geometrically by putting this cutoff in this extra dimension, z direction. This is a version 1, and the version 2 is a time-dependent version, covariant version. So previous one is only can be applicable to static space-time, but we wanted to discuss the covariant version. And then here is the formula looks very similar, but we need somehow little bit difference here. So it's not minimization, but actually extremalization. So we have in mind some asymptotically ADS space-time. We have some boundary, and we pick a particular time here and calculate some surface. But this surface, we cannot minimize area because if we go to the null direction, so this is Lorentzian space-time. So if we go to the null direction, right-like direction, area vanishes. So this is not good. So it's degenerate, trivial result. So we want to find some other surface. But this is a very nice candidate. This is extremal surface. We just calculate area and just extremalize. Don't require maximum. Actually, it is maximize. We have to maximize in time direction, but we have to minimize in spatial deformation. So this is a extremalization means. But sometimes we encounter several candidates of the surface. In that case, we just pick up minimum area. So among discrete choice, we just take minimum area. So this is a covariant holographic prescription. And that case, this is time dependent. Also, wave function is also time dependent. And after tracing subsystem B, we have some time dependent reduced density matrix. So entanglement entropy also time dependent, as also obvious from this picture. This is a time direction, and there are some time evolution of this. And so thinking this way, today I'd like to think third version of this possibility. So this is a third version question. So we talked about static case and the Lorentzian time dependent case, but there are one thing more, one thing remain. That's a Euclidean time dependent background. So this is like you can imagine some Euclidean path integral, and you have some Euclidean time dependent source, and that's definitely we can apply ADS-CFT correspondence. And in that case, we can naturally define minimum area surface. This case, we don't need to extremalize. Just we can talk about the minimum area. And the question is, what does this minimum area correspond to? So what is some quantum information, for example, theoretical interpretation, especially in the conformal field theory calculation? What kind of quantity in conformal field theory correspond to this minimum area in Euclidean time-dependent background? And so analogous, we can ask analogous question also complexity. So so in complexity already discussed by Loeb and Rennie, and so this complexity is also related to minimum volume, maximum time slice volume. But this is a Lorentzian space-time. And but here we are talking about Euclidean time dependence, so we can talk about minimum volume in our set. I think there are some questions. Could you ask a question?
Hi.
Yes.
What do you mean by time dependence in a Euclidean background?
So you can imagine some Euclidean path integral in conformal field theory, and you can take some source or a metric, background metric or background source to some coupled to some operator to be Euclidean time dependent. So you can define path integral in time dependent background that way. Okay. I will give one simple example later. And okay, so now we'd like to consider this problem. And here is a guiding principle. This is just a well-known guiding principle. So at the boundary of ADS, we have a Euclidean path integral, and this Euclidean path integral is equivalent to the bulk gravitational calculation, some partition function, for example. Both are partition function. Euclidean partition function corresponds to Euclidean gravity partition function. We can just go back to this original bulk to boundary correspondence. And then we have anti-Doshita space again here. This is a boundary and this is the inside. And we have some, actually, we encounter two different states as I write it here. So you can imagine, so this is the simplest example. We put some two operators in the lower half, and we put three operators in the upper half. And that case, actually, so there are two operators lower half, and so path integral from -infinity to t tau equals 0, we measure some quantity at tau equals 0. And this path integral is creates this state. A vacuum state is excited by two operators. But the opposite side, if we look at the upper half, then we encounter this Brown kit, and the other state, it looks like just three operator state, right? Created by acting three operators. So we have some two different states we encounter naturally in this Euclidean time-dependent setup. And this is a point. And anyway, we want to compute some minimum area at tau equals 0, and we want to think about its holographic interpretation. So we have to take into account these two different states. So actually here, I just first give our answer to this question. This actually comes from this natural answer, which comes from the consideration based on replicatory calculation of entanglement entropy. And it's actually, this is a similar quantity as entanglement entropy, but a little bit different. So this, if tau is the same as just rho A, then this is a rho log rho, it's a von Neumann entropy. But here we have to use other matrix here, tau A, which is actually transition matrix, just explained here. So it's also depend on two states, bar phi and psi, as we saw here. So there are final state and initial state, these two states. And what the definition of this tau is defined here. So we start with transition matrix. We have some two state bar phi and there's psi here. And this just written this way. And we divide by this normalization so that this tau, trace of tau is 1. This normalization naturally comes from replicatory calculation of entanglement entropy. And then we trace out some region B as usual. And this defines a reduced, not density matrix, but a transition matrix. And just plug this matrix here, then that corresponds to this surface area, minimum area. And so this is not so familiar in quantum information, for example, literature, as far as I know. But for example, I can find some interesting paper by these authors that they define using this transition matrix and some conditional entropy. So this is actually related to the post-selected state. I also come back to this later, but define some quantity. But of course, we have to notice that this matrix is not in general Hermitian. So we have to be very careful about this definition. Okay,
I have another stupid question. Maybe I'm just not familiar with some, issues. But where do these two states come from? You're saying two states come from?
It's come from path integral. So we have some. This is a path integral from plus infinity, minus infinity to plus infinity. And we want to just middle time, tau equals 0. We want to measure some quantity at tau equals 0. In that case, initial path integral gives initial state. And final path integral from plus infinity actually gives final state. So we encounter two different states naturally because we cut path integral into half, right? Upper half and lower half define two different states. Okay. Okay, so yes.
Can I also ask you a question? How should I think about this quantity intuitively? Like, is it some meaning of an information loss?
Very good question. So I will give some what I know, what we find in our work later. But it's not so easy to say, but at least this is related to quantum entanglement. It's anyway, for example, this entropy is related to quantum entanglement of psi and bar phi. There are two different quantum entanglement for this state, but they are related. If one of them is disentangled, this quantity turns out to be 0, for example. But also there are some non-trivial. It seems this quantity also captures some correlation between these two states, psi and bar phi. But it's not so easy to say, relate this quantity to some quantity which we know very well, like mutual information or some other correlation measure. It's not easy to do this as far as, that's quite good, interesting, point, I think. But anyway, I will give some what we find in our calculation.
So may I ask, how do you compute log of this matrix if it's just an arbitrary matrix when you take it?
Yeah, good question. So especially this is because not Hermitian, but nevertheless, we can define eigenvalues. This is one definition. But of course, in general, we have to use some very complicated diagonalization with some even off-diagonal element. And that case, anyway, we can still define this quantity just picking up diagonal value of this eigenvalues. But somehow in holography and this quantum field theory case, we encounter simpler situation. This matrix is not Hermitian, but this quantity is quite well defined by taking, or initially we take a tau to the nth power and analytical continue to n equal 1. This actually works in the example which we mainly work on. But it is true. So there are some very, I'll come back to this classification, but there are some kind of very subtle case. That's right.
There was a question in the chat if this definition can be extended to deal with mixed states?
That's a good question. I'll come back in the end of this talk, and that is closely related to also complexity.
Another question, Tadashi. Hi.
Hi.
Do you really need to have Euclidean time here, or can you generalize it to Lorentz signature?
Yeah, Lorentz signature, we have this kind of, as you know, like we have some covariant case. This case, we just take a single state. As far as we think about this, I mean, holographic dual, so this kind of two state only appears in Euclidean path integral. But it is true. So because this quantity, you can think this is a kind of time, you can put some time evolution of phi t and psi t. Then of course you can define some time-dependent version of this formula. But that corresponds to more complicated geometry, I think.
Thanks.
Okay, thank you very much. Question. Okay, so this here the content I just finished the introduction, gives some basic definition and give some analysis for in qubit system, and go back again holographic issue, and finally talk about complexity counterpart of this quantity. So yeah, so this here just I already gave a definition. So this we start with transition matrix of two different states, and we trace out some part, and we define. We can also define the linear counterpart, right? Tau to nth power. This is useful for replica method calculation. And and we can talk about the basic properties like this. And so as David mentioned, but if we can precisely show that either psi or bar phi has no entanglement, that means just direct product set, that immediately it follows that this quantity, this new quantity is always zero. And this quantity also, because it's Hermitian, so related to the question, it's not this quantity, this tau A is not always Hermitian. If this is Hermitian, this is essentially similar to standard entanglement entropy. But if this is not Hermitian, so in general, it's complex barrier. So this in general, this quantity is complex barrier. But if we flip psi and bar phi, as you can easily imagine, it's complex conjugate. But fortunately, our holographic example always gives, I mean, real barrier because it's area. And also we have some analog of SA equals SB as in the previous question. So we only focus on pure state version of transition matrix because this is pure state transition matrix, as you can see. So we always have some analog of SA equals SB relation like this. And if psi, bar phi, and psi the same, this is just same as standard entanglement entropy or linear entropy. This is just same reduced density matrix as usual because we have symmetric definition of this matrix, so it's the same. And the one comment is that in quantum theory, so sometimes we consider this kind of off-diagonal element of this operator. So namely, in the case of post-selection. So this psi is the initial state, and finally we only restrict the case. Somehow after measurement, we only end up with bar phi, and we just restrict to such a case. That case, so what's the value of OA? And that is something called also weak barrier, known in quantum information literature. But this also takes, in general, even though OA is Hermitian, this quantity also takes, in general, complex barrier. So we are talking about some entropic analog of this quantity. But yeah, this normalization is quite important here. And so we can say a little bit more. And actually, holographic pseudo entropy, which I just defined as a minimum area surface, and it's interpreted as actually weak barrier in the sense of area operator. So area operator nowadays is very heavily used in the context of area safety. And the area operator basically just operator which measures the minimum area. And we can rewrite also this way in holographic context. Okay, so
Sorry, Tadashi?
Yeah, yes.
Quick question. So in your last formula here, I guess both quantities are exponentially suppressed, but the ratio is order 1.
Actually, yeah, yes, I think that also that case you can think about that case, but also you can think about some operator excited state, and you can put some same operator but different position. That case, this off-diagonal element is not completely suppressed. It's not because it's a descendant. It's kind of there's some integral structure. Yeah.
I see. Thanks.
Yeah. Thank you for the question. And so yeah, now I go back to the more basic point, just classification. We try to classify this tau A for 2-qubit system. I'm not going to detail, but it is maybe there are other classification possible, and depending on the focusing on different aspects. But we find some kind of this five-step structure. So this is a general state, And the first class A is tau A to the nth is real value. This can be negative. But this negative entropy negative sounds a strange state. So that means a very exotic state is sitting here. But now we go to the more holographic state or Euclidean path integral state that always gives nice entropy. Entropy is turned out to be always positive, non-negative. This is a class B. And we can go further, or we can just talk about the eigenvalues of tau A, density reduced transition matrix. This is a positive definite. Then this is a class C. And class D and E is a kind of best case. This tau A is a Hermitian. It looks like similar to the entanglement entropy standard case, but it's different because tau A it also depends on two different states, and the states are different. Psi and bar phi, they are different. But nevertheless, sometimes we have tau A is Hermitian in nice example. Now in that case, we have a nice kind of LOCC interpretation. I'll come back to this later. But for the main interest, our case is like holographic, somehow described by single geometry in holography that corresponds to this BCD E. But I'm not, so this other case, more general case is not completely so much explored. It's interesting future problem. But we can think about, we can take just random state that covers everything and see how it behaves. This is a very rough idea, but we can, and this is standard entanglement entropy. So we can have some, this dimension A of dimension A is 8 and B is 32. And we can try many different samples like this. And we can calculate this entanglement entropy. And for example, this case we have a nice sharp peak. And this is very important in the analysis of stage cover. People talk about typical state and the behavior of entanglement in typical state, and we can nicely define. But for pursued entropy, so we have a little bit broader kind of a peak, a weak peak in that sense. But somehow also imaginary value, so we don't want imaginary part. Of course, in general, it has an imaginary part, but it's like, I mean, symmetrical. So it's like it seems this is a very weak peak, but somehow peak value is something physical value somehow. How do
you make the ensemble of the?
Yeah, you can just randomly. It's hard random, basically hard random. But of course we do it in numerics, but using some algorithm to generate this random state. But actually, so yeah, in my talk, let me focus on not the general random state, but it's like this BCDE state. And so here is that one. So that, but especially class E is a best case. The tau A and tau B both are actually Hermitian, but of course different. Two states are different. And in that case, but we have some nice properties that this entropy can be regarded as a somehow again distillation in terms of distillation by LOCC. Yes.
Regarding the previous page, do you have any intuition on how the tail would go down with the size of the system?
Good point. And as stated, but it's not like Gaussian actually. It's more power law like decay, and it's so different from entanglement entropy case. So yeah, we don't have a better understanding more than that.
Okay, thanks.
Yeah, that's a good point. Yeah, but somehow, yeah, structurally it looks really different. And yeah, so the claim is that, so this pursued entropy, it's defined some very mathematical way, maybe previously, just low log law, analog log, just we imitate low log law, tau log law. But actually it seems to be the measure, it measures the distributable Bell pairs in intermediate states of post-selection procedure. So we assume final state is bar phi, and just in that case, we just restrict that case, then just estimate average number of Bell pairs, then we find this same behavior, same formula of this entropy. So I'll explain it. And so this class E is very simple. So 2-qubit case, we just focus on this nice diagonalized state with different angle. Of course, these two guys are different. Theta 1 and theta 2 different, and here it's a plot. And so this is a transition matrix, and this is just honest calculation of this tau log law entropy, pseudo entropy. And here is some interpretation. So this we just follow, or I mean, very famous argument of this how we can extract entanglement from many copy of qubit systems. Just this leads to the explain this von Neumann entropy formula. And so we have we can just focus on one particular state, then psi state like with theta 1 angle. So then we can take a M copy, this asymptotic limit, and we expand in terms of some maximally entangled state. So there are two M spins, right? There are two qubits and M copies, so two M spins. And this A consists of M spins, and B consists of M spins, and they are maximally state, maximally mixed, maximally entangled state. And these are very simple bases actually. So K is a number of 0, K is a number of 1. So we have 0, 1, right? 0, 1 qubit state, and 0, 0, 0, 0 means K equals 0. Just one of them is 1, then it's K equals 1, but there are K different possibility, right? When we put 1, right, inside M spins. So there are M number, but in general, if we have a K1 and M minus K0, in that case we have a combination, right? We have possibility of CMK possibilities, and that this part, this number of these states appears. And we have some linear combination such a maximally entangled state, so we can just, we can do some, a projection. This is part of LO operation that we can project down to particular maximally entangled state. Then we can say this has an entropy log MCK, right? And we take average. There are many possibilities of this. It's a linear combination. So each possibility is turned out to PK, right? Given by this. C1 or C2 is just cosine theta 1 or sine theta 1. And so I take average by PK, and then we have this number of their pairs. Then we find actually M times, and we can find this pseudo entropy formula is recovered in this taking this average, because this average is just turned out to M times pseudo entropy. M is an original copy number of copies, and we take M the average number is this pseudo entropy. So this is just kind of generalization of this well-known relation. So at least this particular case, it seems to have some nice interpretation. But in general, of course, this quantity takes complex value. So that case, we don't know precisely. And yeah, anyway, so these are what we understood for this quantity, at least in our initial investigations. And so now I move on to this holography. So holographic pseudo entropy, already I mentioned definition. So we have a Euclidean time-dependent background, and we pick up some minimum area surface like this, and gamma A. Some of this minimal surface is gamma A is time-dependent, Euclidean time-dependent. And this, of course, this minimal surface is, of course, non-negative entropy. So this corresponds to non-negative pseudo entropy, which means very special state, of course, as we mentioned. It's a general, it's complex value, but let us focus on that case. And we can quickly see some basic properties of this holographic pseudo entropy. For example, that everything is a pure state. This is lapped A is lapped completely everything. So that means no surface remains. So that's entropy 0. And we can also see either psi or bar phi is not entangled. For example, putting some extra boundary. This is something what I call this ADS PCFT prescription. We just cut out space-time here. We just regress the other part and replace this with hard wall. Then entropy turns out to be 0 because this surface can end up just shrink to 0 size here. And so we can SA equal SB also obvious as usual in entanglement entropy case. And subadditivity, I think you can also easily see, because we have this definition includes minimum. But the strong subadditivity is not clear for this case. And also, in general, if we just study in general qubits, we can easily see strong subadditivity in general violated. Some analog of strong subadditivity for pseudo entropy is violated. But somehow, as far as we see in phenomenologically, some just explicit example, holographic pseudo entropy, we don't see any violation so far in explicit example, but we cannot apply very famous proof by Alan Wall by using this max-mean prescription of this covariant entanglement entropy for time-dependent case. But for our case, it's not mean, so we cannot use this proof. So this is a kind of open problem. But also, I didn't mention so much about derivation of this formula, but actually this equivalence actually is quite obvious from the viewpoint of this Lukovic-Marda-Sena derivation of holographic entanglement entropy based on Bark-to boundary relation, because we can think about this kind of replica calculation. So just new twist of this replica calculation, we have two different states, right? Bar phi state created by this operator, and the psi state is created by this operator, and bar phi state is another operator, but with inserted in different location. And but the replica trick is the same. It's just standard trace tau to n. We just paste this n seeds into each other, but the excitation point is different. But you can imagine from this, and just thinking about standard analysis of holographic calculation of this Bark partial function, we can simply just recover this equivalence. Okay, and this is also from viewpoint of field theory, this quantity also well defined because it's positive. This partition function within some reasonable background is of course positive. Okay, so and we can talk about some example. So this is genus background. So this is like inhomogeneous excitation. So we have like this Euclidean time, but tau less than 0, we have some particular perturbation by this exact minor perturbation, phi minus. And later time, we have a psi plus perturbation, different perturbation. And so it's like inhomogeneous in time direction, no time translation invariance. And that case, it's, and we can particularly focus on the simplest case of ADS2, so ADS3. That case, we know the nice solution back at Parhirano. This is a very simple analytical solution, and we can just use this solution for example. And this case, this path integral prepares final state and initial state is by different perturbations. So these two guys are different. And we can just calculate the entanglement entropy at tau equals 0 by picking up minimal surface, but which turned out to be the same familiar minimal surface, namely semicircle. And then we have logarithmic divergence because it's related to DCFT, but coefficient modified. And it's like also, if we take a perturbation, gamma is this deformation parameter. Gamma equals 0 means these two guys are the same. These are standard entanglement entropy. This final state and initial state is different. But gamma means that if we put gamma initial state and final state is different, and we get a reduced value of entanglement entropy. Effective central charge seems to be changed. But this kind of a result also, we can derive this result from CFT perturbation by using tape recording because it's consistent with this holographic prediction. Okay, so these are a simple example, simplest example of holographic calculation. And so we can, there are questions that about this about mixed state, and this is also quite useful to define complexity. And so what about mixed state? So one starting point is look at this tau AB. So total system AB, and there are maybe C. If we put some C, then maybe everything is purified. But let's forget about C. Then it's like a mixed situation. And AB, tau AB, psi, bar phi, and phi. So if we put C, this psi and bar phi is pure, but it's we trace out C, then it's always mixed. And in that case, can we define just the whole entropy for A? We are interested in bipartite correlation between A and B. In that case, if we define some Pseudo entropy for A, how can we do this? But there are many, I think, approaches for this case, but let me give one of them. It's like using the purification, canonical purification. This is also used in the reflected entropy calculation by Dutta and Holkner. And we can use a similar ideas. And this we can, if we have some operator, not necessarily unitary, but we can just always purify it by canonical purification. Just this is a definition. It's a complex conjugate state. And we can define this using this and Pseudo reflected entropy by this formula. So now it's tau, square root of tau, but it is, we have put dagger here. This is, so that means it's not symmetric. It's not standard density matrix. It's like, again, we encounter kind of reduced transition. We encounter some transition matrix here. But this, once we adopt this prescription, we can also generalize the result for this Dutta and Holkner, namely, this reflected entropy is equals twice of entanglement wedge cross section. So there are other proposals, including ours, like related to entanglement purification or entropy by Kamoko. But here I just talk about the reflected entropy. In that case, we have twice of area cross section. But we can generalize for our case. If we take this generalize some Pseudo reflected entropy, also this is turned out to be twice of this entanglement wedge cross section. And so this actually technique also we can try to understand what about Pseudo some complexity. So I just maybe put just name Pseudo complexity, but this may be a little bit confusing because already as in Lenny's talk, so Pseudo entropy is introduced by Boreum, Pfefferman, and Bazzarini about some kind of coarse-grained version of complexity to explain some puzzle and what they propose. And but here we are talking about Pseudo entropy for two states. This is just a generalization of Pseudo entanglement, Pseudo entropy. So these two guys are so different, it's, completely independent. So maybe this is not good way of calling this quantity, but we don't have a good idea. So anyway, so the question is, what is the complexity of transition matrix as we asked for entropy? And so we can talk about this by purification, canonical purification. So we can define pseudo complexity is a kind of complexity of pure state, the square root of this tau, which we introduce here. So anyway, and this is closely related to the idea of the subsystem complexity by these authors. There are many works in this section. In that case, if we talk about reduced density matrix and their complexity, we have to purify anyway. So this is somehow common issue. Yeah, we just pick up particular purification. Maybe we have to minimize all possible purification, but we don't do it here, or just the whole simplicity. And then we can try simplest example, that means pure state case. So now it's A is total system, and then we can somehow try to follow the idea of this complexity equal Boreum by Lenny in a Loeb's talk and Lenny's talk. And so in our context, we are in Euclidean setup, so we don't need to maximize. We don't need to look at maximum time slice, but we have to look at minimum time slice. Minimal time slice volume. This is more naturally defined. And we might say this pursuit complexity might be equal to this guy. So this is maybe one, simple-minded conjecture, right? We have some bar-phi state and psi state, and they are non-trivially back-react geometry, but we just pick up minimum slice and minimum volume might be compute this quantity. But however, we find some problem about this. So if we take this pure state case, very simple, psi and bar-phi, and we can take this canonical purification, just turn on psi and bar-phi star, just this is independent, right? Completely factorized. That case, it's obvious. Of course, we can have a many different ways to define complexity, right? Using Nielsen's method or discretized quantum gates, or also our path integral method, path integral optimization. There are many different ways, but always, I think this answer to this question, it should be just sum of these two states, right? Because this is so simple, looks simple. But on the other hand, if we look at this naive Boreum conjecture, then, so these two guys are non-trivially back-react. So it's not, we think this is different. I mean, we think this is not just sum of these two contributions, right? So it's the psi case, we have back-react geometry, and another back-react geometry is bar-phi, and we can compute Boreum, but it's not, just to give these two guys, but it's not probably not equal. So that means because more gravity is more non-linear. So in that sense, this naive, our generalized version of this complexity Boreum may not work. I'm not so sure, but it seems that this case is really puzzling. If you have any opinion, that's very, very welcome. Please discuss later. And so we can also try another example, which we can simply calculate. That is maybe sum field out. I think people usually start from sum field out first. And that case, this transition matrix turned out to be this one, because we two different beta 1 and beta 2, two different inverse temperatures. That case, after combining these two, so reduced transition matrix turned out to be temperature is average, beta 1 plus beta 2 over 2, so complexity looks like this. But this itself seems to be nicely consistent with holographic nature. Even we can take complexity Boreum, but this really take into account nice back reaction. Right? Beta 1 geometry and beta 2 geometry, they are non-linearly back react, depending on the periodicity. Okay, so and then finally, I just wanted to comment that so far this naive approach maybe. So if we just want to think about this minimum time series Boreum, what's the counterpart in CFT? Then maybe there are other candidates, which is like something which we call information metric. It's like Fubini style or maybe Bress metric. And also there are sophisticated version of this. It's more precise argument by Belin, Lukowitz, and Saroshi by using very interesting definition using some different time choice in gravity. But here I just talk about very rough argument, so that we talk about some conformal field theory and exact marginal perturbation, and then we have some parameter lambda. And if we have a parameter, and the ground state is parameterized by lambda, and if we have a state parameterized by some parameter, we can define information metric. This is just a standard definition of information metric, and it's a deviation. D lambda is infinitesimally small, then coefficient of D lambda square is an information metric. So if this D lambda is 0, this inner product is just 1, right? So distance is 0. This Bress distance is 0, but its small perturbation gives some square quadratic perturbation. That coefficient is in this information metric. In that case, actually, in this quantum field theory case, we have this integral 2-point function. And here in our previous work, as we conjecture this is related to some volume of this minimum time slice, maximum time slice volume in some Lorentzian geometry. But we are in a Euclidean signature, so we talk about minimum volume, and it's more, you can see more precise stories here. But anyway, so here just to talk about this rough sketches enough. So this is a holographic relation, and we can imagine similar formula also true. Same formula is true for our transition matrix, so that the initial state and the final state is different, bar phi and psi. And still we can talk about this genus like background, and then we can just pick up this volume. And then we can imagine this is related to information metric. And this case, I think it is consistent with this inequality. Right? It's non-linearly back-react, so this geometry is non-linearly non-trivial. So this, if we just pick up this volume, it's non-trivial. But also this quantity, 2-point function, also depends on initial state and final state. It's also non-linearly. It's also non-trivial. You get a non-trivial metric. So maybe this gives some improved discussion, improved version of this minimum volume. But yeah, it's quite open. Still, this kind of open issue. Okay, so so it's good. I already spent some time, so for my talk, too much time. So just let me finish my conclusion. So so the main claim of this talk about the entropy, about this is the area of minimal area surface in Euclidean asymptotical areas with time dependence. And so in general, this quantity is complex barrier. This is a little bit problematic, but somehow holographic situation described by single geometry is always not positive. And also Euclidean path integral seem to give us some reason. So Euclidean path integral with a reasonable background seem to be always give some positive barrier result. And so this pseudo entropy also, we talked about some very good class of this cubic system. So pseudo entropy can be regarded as some just number of EPR pairs, Bell pairs, in some post-op selection procedure, some intermediate states. And it's quite interesting to think about more general class of state. What about the interpretation of this? Maybe we can, so what's the minimum also complex barrier and so on. And finally, we talk about, as in this workshop, I talked about the complexity, idea of pseudo complexity, some transition matrix complexity, and we give some simple definition. But this simple definition is somehow, I'm not so clear that it's how much it's related to this volume. But anyway, definition is I mean, we can use the standard calculation by many others, also many speakers in this conference, that we can use a result and we can estimate also this transition matrix complexity. And it's quite interesting to see what happens in its holographic counterpart. Yeah, thank you very much. I think I will stop here.
Okay, thank you very much. Let's maybe unmute to thank Tadashi. And,
Thank you.
Thank you.
so we can have a few more questions if there are any. I have one. Oh, okay, sorry.
No, you start, I'll go next.
So if the Euclidean path integral automatically gives something real and positive, wouldn't you think that maybe it has to be interpreted as a quantity which is always real rather than something which can be complex?
Yeah, actually, so yeah, it is true. So Euclidean path integral with a real valued source always gives positive value. But also, at the same time, we can create such a state, and we can create another Euclidean path integral and create another state and take a linear combination between these two states. This is of course possible in quantum mechanics, and with some complex coefficient. And that case, it is easy also see that this pseudo entropy turned out to be complex valued. So somehow, but each real valued path integral seems to be correspond to real valued Euclidean geometry in ADS-CFT. So we have some single classical gravity duals, and we can also take linear combinations of that. And if this linear combination is complex valued, also again, we get complex valued pseudo entropy. So it seems there are some nice bases where a pseudo entropy is real. So maybe yeah, if we can just focus on that, then we have a nice story. That's yeah. So thank you for this clarification. Yeah, that's quite an important point. Yeah.
Shiran, you had the question.
So I wanted to ask. I guess like when I'm thinking in the Euclidean, like would it make sense for me to rotate the time direction and think about it as a space direction? And if in this case, would it have any other interpretation? So if like, can I define a pseudo entropy quantity, but in a space, like with respect to some kind of space evolution, maybe?
Space evolution. Okay, but that case, but how we need to specify a state. And in that case, we need whole space to define wave function.
Right. Maybe I'm thinking like, you know, between evolution between two boundaries, like overlap of states between two boundaries of a cylinder, of a spatial cylinder.
Two boundaries. I see. Yeah. I think, yeah. I mean, basically, so so in that case, but probably we can start with two different path integral from the beginning. Maybe they can also interact with each other sometime. But in that case, I think if you have two different independent path integrals, so either of that define some different states, and we can define this quantity, indeed. Yeah, I think that's interesting. Yeah, definition.
There is a question in the chat. Could you please explain the idea about pseudo complexity a bit more and why you have said? Wait, it's not finished. And why you have said complexity volume conjecture may not work.
May not work. Yeah. So this is a kind of a simple observation. But let me. Somehow. Okay. Yeah. So here. This is an observation that anyway, so if we assume pseudo complexity also volume, then we start with two different states, right? So here we have two states, bar phi and the psi here. Okay, bar phi and psi, and these two guys give us a non-trivial different boundary condition at infinity. Maybe you can put 3 operator excitation, 2 operator, and that case. According to this excitation, it back reacts quite a lot of geometry, and we have a very non-trivial geometry here. And if we have some only psi and psi, both are initial state and final state psi, then we have only 2 operators and non-trivial metric here. It's different, completely different from this guy. And then if we compute this area, or volume here, so this volume and this 3-point excitation volume, it's not related to anything of this volume. So that's a reason. So we get some. So we get a non-trivial contribution from back reaction. So we don't expect this simple relation between volume of this guy is just sum of these two guys. So this is basic argument why I'm saying this simple formula we cannot see in this naive volume conjecture. Is this clear?
Well, I don't know who was asking. Sayantan. Maybe he can say if he's satisfied.
Okay, yeah, thank you.
So
yes, it is clear. Okay.
So I was trying to understand what's special about family of states where the pseudo entropy is positive. And one thing from the holographic point of view, one thing that's special about the states where all the Euclidean sources are real is that from the Lorentzian picture, it's all the conjugate momenta are set to 0. So if you think, if you think about describing a state as, extrinsic quantities on a Cauchy slice, then you have the metric and the extrinsic curvature. If you have a scalar field, you have the value of the scalar field and the derivative of the scalar field with respect to the slice. And so these states where all the sources are real, they give you configurations where all the momenta are set to 0.
Momenta.
Yeah, the canonical momenta.
But what I mean is in Euclidean ADSF setup, we have supergravity, Euclidean supergravity. And if we assume all field value in Euclidean supergravity is real, then we have also metric is real, also this quantity is real.
Yes, I agree, it's real, but I think it's zero. Just by Z2 symmetry, if you think about states that are prepared, with the real sources in a Euclidean path integral, then I think you'll get all momentas are zero on the slice. So I was wondering if there's something special about that.
So, but in this, pseudo entropy case, actually, there are no G2 symmetry, right? Tau equals 0.
No, I understand. I'm just saying, if you think about the states themselves, if you just think about psi and phi, you have a huge family of states where.
What's special about this state?
I'm saying, what's special about this state? And one thing that I can see is all these states are such that all the momentas are set to 0 in some sense.
Okay, I see.
I was wondering if there's
real value of field, right?
Yeah.
Okay. Yeah, but it's, anyway, the real value of field is quite clear from this Euclidean path integral. I think it's related to the source is real.
Right.
So we restricted that case. I think probably equivalent to what you're saying.
Okay, maybe if we are not to go too much behind schedule, we can postpone after more questions to the discussion after the next talk. Is that okay?
Thank you very much.
So let's thank Tadashi again for